Imagine you are a registrar drowning in a sea of student scores. You need to calculate the average of the top 5 marks for every single student, but the data is messy and unsorted. How do you extract just the best 5 scores for each person without getting bogged down by the noise? Let's solve this efficiently. You receive a list of records, where each record contains a student ID and a score. Your goal is to return a list of student IDs paired with the average of their top 5 scores. If a student has fewer than 5 scores, average all of them. The output must be sorted by student ID. The core challenge is filtering the top 5 values for each unique ID from a potentially massive, unsorted dataset. The naive approach is straightforward but wasteful. You'd group all scores by student ID into lists, then sort every single list in descending order to pick the top 5. This forces you to sort thousands of scores even if you only need 5. The time complexity balloons to big O of n log n, linearithmic time because of that full sort, and you store all scores in memory, making it inefficient for large inputs. Here is the key insight. We don't need to sort everything. We only need to keep the top 5 scores. For each student, maintain a min-heap of size 5. As we iterate through the scores, if the heap has fewer than 5 items, we add the new score. If it is full, we only replace the smallest score in the heap if the current score is higher. This ensures the heap always holds the 5 best values seen so far for that student. After processing all items, we simply empty the heap, sum the values, calculate the average, and store the result. Let's trace this with the first example. Student 1 has scores 91, 92, 60, 65, 87, and 100. We start with an empty heap. We add 91, then 92. When 60 comes in, the heap has space, so we add it. We continue adding 65 and 87 until the heap holds 5 items. Now the smallest is 60. When 100 arrives, it is larger than 60, so we evict 60 and insert 100. The heap now contains 91, 92, 65, 87, and 100. We repeat this for student 2, evicting low scores as better ones appear. Finally, we sum the heap contents and divide by 5. The final output gives us student 1 with an average of 87 and student 2 with 88. This is correct because we successfully isolated the highest 5 scores for each ID, ignoring all lower values that would have skewed the average. You'll spot this pattern whenever the problem asks for the top K or best K items from a stream of data. Specifically, look for a fixed limit on how many items to keep, or a requirement to discard the smallest values when capacity is exceeded. Time complexity is O n plus s log s, where n is the number of items and s is the number of students, since we only sort the final averages. Space complexity is OS to store the heaps and the result map. Try the next problem involving top K frequent elements using the same heap pattern. Don't forget to subscribe for more DSA deep dives.